Hi, the sections 12.7, the analysis of covariance. So analysis of covariance, or the ANCOVA, is a mixture of ANOVA and the linear regression model. So we have basically both the continuous and the categorical predictors. And this tests the difference in coefficients of linear model across groups. So we have categorical variable. So in some sense, for each category that we have the regression line. So we would like to test if those lines are different or not. So the setting is here. So there are k two or more the populations. For example, the one control group and the one group for the treatment 1 and the other group for treatment 2. And the variable y and x are linearly related for each population, but the relationship may be different among populations. So that means the y is equal to beta not 1 plus beta 11 x plus epsilon for population 1, but for different population, we have different parameters. Maybe this is k. So these coefficients may be different, or these coefficients may be different. So our objective is often to test if beta 11 to beta 1k are all the same or not, or also this intercept beta not 1 to beta not k are all equal or not. If all equal, then we may want to test if the beta 1, I mean the coefficient of x is equal to 0 or not. It is not common to test if intercept exists, so probably we can ignore this one. So in the context of ANCOVA, that we consider this model. So basically the mu I is the mu I times, maybe to be exact, this is the summation of mu I times indicator variable of category I. Indicator for category I. Population I. So we have some baseline intercept plus the mu I. So this is the additional the intercept for category I. And also the same thing for the coefficient of x. So the beta 1, so that is the common, so baseline slope, but also that we have the slope for additional, the slope parameter for the ice population. So often we want to test if this is significant, beta 1i are different or not. And also we want to test if the mu I is equal to all 0 or not. And if these are both not rejected, then maybe we set these as 0, then we may test the beta 1 is equal to 0. And this the beta 1i, so this term, this is called the interaction term as in the two-way ANOVA. So this is because we have the interaction between group and slope. So basically the x affects the value of y, but also the group affects the value of x. So we have interaction between the group or category and the x. Yeah. And usually we need a baseline. So usually we set the mu 1 is equal to 0 and the beta 11 is equal to 0. Otherwise, we have the too many parameters. So if we have I categories, then beta naught plus mu I, and we have beta naught and mu 1 to mu sub capital I, then we have basically I plus 1 intercept for I groups. So that we have the too many parameters. So usually we have to set one parameter equal to 0 So that means we have to assume either mu1 is equal to 0, or sometimes the summation of mu I is equal to 0. The same thing for beta 1. So we can either set the beta 1 is equal to 0, or the summation of the beta 1 I over I is equal to 0. So we need some restrictions. Yeah, so this is an example. So this is from the library ISWR. This is the library developed for the textbook, and we use this HELL. Excuse me, the HELL-LANG, the data set, and this is have the basically the three variables: the glucose level, and the this is the concentration, and the diameter, cell diameter. So yeah, so basically we wanna see, we wanna explain this diameter by other variables. So this is basically y, and we have x here. Then this is the groups, the populations. So we wanna regress y on x, but also the groups, the indicator variables for groups. And we have the only two groups here, group 1 and group 1, the glucose level 1 and the glucose level 2. And x and y are continuous variables. And this is the scatter plot. And you can see that the for glucose level, the 0 and 1 and 2, we have two different groups. And if we think about the trend line of this no glucose group, probably trend line is around here. Okay, and for circles, the glucose group, probably the line is here. So the both have linear relationship and probably the same slope, but the different intercept. So our question, research question, is whether these two curves, these two fitted lines have the same slope or not. So I mean, if these slopes are significantly different or not. So the model is here. So diameter y is equal to beta naught plus mu I. Mu I is the intercept for the coefficient for the indicator variable for ice group. And ice is a 0 or 1. 0 is for glucose, 1 is no glucose. Plus the beta 1 plus beta 1i times the log of the concentration plus epsilon ij. So our interest is whether or not slopes are different. So that means we want to test this beta 1i. Since the baseline should be 0, mu1 is equal to 0 and beta 1 is equal to 0. So here we only have two groups. So basically we want to test if the beta 1, 2 is equal to 0. So this is the null hypothesis, and the alternative is beta 1, 2 is not equal to 0. Yeah. And it can be done by ANOVA. So at first, to fit this model, diameter on log of concentration plus glucose and this interaction term. So basically, we want to test this. Yeah, equivalent. So we have the interaction term. So we used the multiplication symbol, but also that we can write the log of concentration colon the glucose. Then we have the three parameters here. So all have just one parameter. If we have the more than two categories, then we have the two level of the glucose in addition to the baseline. But here we only have the 2 levels of glucose, and concentration is continuous variable. So we only have the 1 parameter for log of concentration, and 1 parameter for glucose, and 1 parameter for interaction. And you can see that the log of concentration is very significant with p-value the 5.9 times 10 to the power negative 10. And the other two are actually insignificant in this model. If we drop one, maybe the one becomes more significant. But at this point, we are not sure if these two are really significant variables. Yeah. So this is the regression result. Yeah, but two coefficients are insignificant, but we are not really sure if the both are garbage or just if we drop one, the other becomes significant. And if we drop the interaction time and we only use the log of concentration and glucose, actually these two variables are both highly significant. So basically the glucose and the interaction between glucose and log concentration, those two have multi-collinearity. So that's why that we got insignificant coefficient for the both variables. But in reality, glucose is the useful variable. Okay, so finally, we want to test if this interaction is significant or not. And as you can see, after introducing two variables, the log of concentration and the glucose, that this interaction is not significant because the p-value is large enough. So you can see, so this p-value is based on this f-value, and f-value is the ratio of this and this. So mean square error. So mean square residuals over this, the mean square residuals. And that is obtained by this sum of square divided by degrees of freedom and sum of square divided by degrees of freedom. So 10 divided by 47 is 0.214. So basically this measures how much of the variabilities total variation is explained by each variable. So that means that originally we have the variation in y, and if we introduce the one variable, we can reduce the error size. We compare the total variation of y and the residual of the regression model, that the diameter on log of concentration. Then actually the total sum of square is the summation of all of these numbers. So, but the most of the part, 129.5, is reduced when we use the log of concentration as the predictor. And if we put glucose in addition to log of concentration, then the sum of squares are explained by this variable, the glucose variable. But you can see after that, if we introduce the interaction time, only a few part of the residuals are explained by the intercept. And finally, the 10.073 is the residuals, sum of squared residuals that remained unexplained by these variables. Yeah, so in this way that we can check the interaction, we can test the interaction between two terms. So that is the application of the chapter 13 and the chapter 7. So we combined ideas of the ANOVA and the multiple linear regression. In this case, the simple linear regression.